Well, hello, B-Day class. Happy Independent Friday. This is kind of an unusual situation. We normally have you learn kind of some different stuff than what we've been doing in class, but because Monday was a day off, we're just a little bit behind. It's not a bad thing at all, but I just thought we'd do our lesson together as a video. So you feel free to fast forward me to make me go a little bit faster to speed it up. But by the time we're done, we're going to turn in the lesson 3.3a student activity sheet, and that's when we'll be all done. So this is what we're doing. We are still looking at the buffalo. We've been looking at the food sources for the buffalo. Remember that we were hypothesizing, actually I can pull it up right here. We've been looking at this graph of the buffalo population and wondering why the buffalo increased in their population. They nearly doubled in size. So what we have been investigating previously is their food sources. So just wanted to remind you what we've been talking about. I did dig up, just because we've seen a lot about wildebeest so far, but we haven't seen a whole lot about the buffalo themselves. So I thought I would show you just a little bit, and I've actually got it, I think, sped up so it will show it a little bit faster than normal. But I just wanted you to be able to see the buffalo that we're talking about.
Brings lethargy to Africa's predators, and they're entitled to it.
I do have the video sped up just a little bit, so the narrator sounds a little funny.
But is a large protein-rich meal, which takes time to digest during daylight hours. Their prey has to remain on their hooves, not only at night, but also throughout the day, in order to maximize food intake for their bulky frames.
If you're not interested in watching this video, you could fast forward through it until we start the worksheet. I just wanted you to see about the buffalo a little bit, a couple minutes.
Grazers. They live in swamps, savannas, and forests, eating mostly grass. Congregating in large herds, buffaloes move quickly through tall, coarse grasses, as these fussy eaters do not like to eat in trampled grasslands.
They're fussy eaters.
It is said that the dietary habits of the African buffalo has not only opened up grasslands for other species, but they are also responsible for the quality of the grass by choosing to eat long, fibrous grasses, which opens up new growth of softer grasses for other grazers.
Interesting. So they have an impact on the food that's available for other grazers.
Are an adult buffalo's only predator, while hyenas and leopards attack calves or the very weak. Razor-sharp horns behind half a ton of strength makes this a formidable weapon and is incredibly effective at defending against these predators. Horns of male buffaloes are large and go on to form a protective bone shield referred to as a boss. Cows and juvenile bulls have smaller horns with no fused base. Horns are used to set order by dominant bulls, and younger bulls regularly take the time to learn the skills they'll need one day.
There we go. I wanted to pause the video for just a second. I hope it's still working. I just wanted to point out, because we had learned about symbiotic relationships, notice the birds that are living on the buffalo, they're eating parasites off the buffalo. So the birds are getting a meal, that's good for the birds, and the buffalo are getting parasites pulled off of them, so that's good for the buffalo. So that is an example of mutualism. We'll see a couple other examples in just a moment. Did it go? There we go.
During resting time, females vote by standing up, shuffling around, and sitting down again in the direction they would like to move in. It is rare to see this kind of communal and not dominance behavior in herd animals. While the general direction is known to the herd, the actual route is plotted by the more experienced cows, who are known as the pathfinders. They are responsible for guiding the herd to grazing pastures as well as water. Buffaloes never stray far from water, as they depend greatly on it and must drink daily.
Here's another example. Look at the bird on his back.
Cattle egrets flock around the herd as the tall grass eaters disturb many insects, which the birds pounce on.
So in that circumstance, the bird was called a cattle egret, and as the buffalo moves, bugs are kicked up, sometimes even small rodents, and then the cattle egret eats it. And so that's beneficial to the bird, but it doesn't impact the buffalo at all. It doesn't hurt the buffalo. It doesn't help the buffalo. So that's an example of commensalism. Do you remember that word? That was from last week. So commensalism. All right, I'm going to go ahead and stop there, and we're going to go ahead and start now our official lesson. So give me a second here to go. So you should go to the page, our February 19 page. And so here's the video that we were just watching. So it says, what did we learn about buffalo, what buffalo eat, and what could affect its availability? And so go ahead and open your lesson 3.3 student activity sheet. Have that open on one side of your screen and have my video open on the other side so that we can just get this done for you together. So let's go ahead. I'm going to assume you're opening it, or if you haven't already. And I'm going to go ahead and go to my Kami sheet, and scroll up to the top, and I'll make this as big as I can so you can see, and I'll type some stuff to give you some ideas. You do not need to copy what I'm typing, but if you are more comfortable writing what I'm writing, that's totally fine. I don't care. So it says, what did we learn last time about the buffalo's food source in the Serengeti? So there were a few things that we learned. Ooh, that's small font. I'll make it bigger next time. We learned the names of the plants, that says pants, the plants that they ate, comma, and we learned that they don't compete with others during the wet season, but they do compete. And remember, they compete with a lot of animals. They compete with wildebeest and gazelles and zebras. So they do compete in the dry season. ... I'll make my fonts bigger from now on. Sorry, that one was so small. Let's go with maybe a 14 point. That should be better. All right, what do we still need to figure out after our investigations last time? So last time we were kind of hypothesizing that maybe this giant increase in the buffalo population had something to do with increased food. But what we didn't know was there increased food, and had the climate changed in some way? We didn't know anything about rainfall amounts or temperatures or anything. So we still need to know about the climate during the time frame. I'll just say time frame. So from 1960 to 1975 or so, when the buffalo were increasing. Again, you don't need to type exactly what I'm typing, but if you want to type it, that's totally fine. So that's something that we want to figure out. So the hypothesis, a lot of folks had the hypothesis that the rains might have increased, and remember, they're not competing during the wet season. So if the rains are increasing during the wet season, maybe there's more and more food, and so we can have more and more animals. Maybe that's what happened. So we have already once before done something similar to this, but now we have more information, and we're going to keep modifying it and making it better every time. It says, if climate change is causing the changes in the buffalo population, what do you predict the graph of the rainfall would look like? Draw it or describe it below. So if you want to write words, that's totally fine. But I would be totally fine if you drew it even on this graph. So this graph has the years. That's perfect. But over here, it's population size, not rainfall amount. It really should say, like, if we were going to add rainfall, it should say like centimeters or inches or something like that. That's okay. I don't care. Just show me the shape that you're predicting. So I think most students predicted, but you draw your own shape. I think most students predicted either that the rain was increasing, so we would see it something like that, or let's see, can I make that one go away? Not zoom out. I want to undo. There we go. Undo. There we go. Or they thought that maybe the rainfalls had been lesser earlier, but that they were just really high rainfall amounts, not that they were increasing, just that they were high rainfall amounts during this time. And so that's what a lot of students were hypothesizing. So next it says, why did you describe or draw the graph in number 3 the way you did? So you need to give some kind of an explanation. I think most people explained it by saying, if there is increased rainfall, there may be more plants to eat, and therefore more buffalo can be born. That's an awkward sentence. Nobody cares if it's awkward. So if there's an increased rain, if there is increased rainfall, there may be more plants to eat, and therefore more buffalo can be born. They're doing better, and so the population can increase. That's what most people were saying. All right, I'm going to move on. You can stop this video at any time if I'm going too fast. You can speed it up if I'm going too slow for you. That's the nice part about the videos, right? All right, so climate data. Let's look at the actual data. Let's find out, did the climate change during that time? Was it a particularly dry season or a particularly wet season or hot, whatever? Let's find out. So the first thing that we're given is a graph that's about the average annual temperature in the Serengeti during those years. So from 1960, it goes all the way to 1979. And so if you notice, there's just this incredible diversity of levels. So it's just constantly, it's fluctuating up and down and up and down and up and down. But what I want you to notice, I'm going to undo that. What I want you to notice is this arrow right here. This line right here. Do you guys see this line that's going across? That's called the line of best fit. You do not need to write this, line of best fit. It's basically an average of all the data points that are all scattered all around. This is called a scatter plot. And then they fit it, they find the average and they run the line through it. So the average temperature here, and what do we notice is happening? I don't see any change in temperature at all. Even though there's lots of fluctuations, the average temperature hasn't changed one bit. So during that time, temperature was not changing. So we could write that easily enough. During the time the buffalo were increasing, temperature stayed the same. I'll resize that here really quickly. There we go. So temperature was not a factor, at least we don't think it's a factor in what's going on here. So that's part of our hypothesis. Now the next graph is the rainfall. And I think that most of us hypothesized that rainfall was either very high or it was increasing during this time. So let's take a look at what it actually shows. Well, again, look at the scattering. Look at how up and down the rainfall levels are. It's quite dramatic how much it varies. But if we pay attention to this line of best fit again, if we look right here for that line of best fit, it goes down. The average rainfall didn't increase when the buffalo were increased. The amount of rainfall decreased. That's not what we hypothesized. That's not what we were expecting. So the average amount of rainfall decreased during this time. All right, so moving on. So the final kind of concluding, pulling it all together. What happened with the climate of Tanzania during the 1960s and into the mid-70s? The climate is a combination of temperatures, rainfall, wind. So what we know is temperature and rainfall. So the climate did not change much. Temperatures stayed steady, and rainfall decreased somewhat. Write it however you want, but that's what I'm going to say. The temperature didn't change much. The temperature stayed the same and the rainfall decreased a little bit. So mostly the climate didn't change. So here's our question, wrapping it all up, drawing a conclusion. Do the trend lines of rainfall and temperature indicate that climate was the cause of the buffalo population increase? And that would be a big fat, oops. No, they do not indicate that. Explain. How do we word that the best way? So if rainfall decreased, we would expect less food for the buffaloes. Is buffaloes ES? I think it is. I think I spelled it wrong. Buffaloes. That doesn't look right either. Well, if you notice that I misspell it, my apologies on that. Okay, we would expect less food for the buffaloes and that the population would decrease. So climate does not seem to be the cause, a change in the climate, so a change in the climate does not seem to be the cause of the increase in the buffalo population. Yeah, good. All right, now we get to move on. We're going to do a computer simulation. You might remember from when we did our unit on bacteria and antibiotics, we had a computer simulation. It's the same program, but it's designed specifically for what we're studying this time. And you have to keep in mind that scientists use computer models all the time. It's impossible for them to take all variables into account in a really complex system. A great example is what's happening right now with coronavirus. There's so many people, there's different types of vaccines, there's different variations of the virus. So how are they supposed to know, numbers and that kind of thing about how can they predict what's going to happen in the future? So they're using computer models. And their computer models so far have been doing a really good job of predicting where the pandemic is going to be. So that's what we're looking at is computer models. So it says you will use a computer simulation to explore what happens to a population of grazers. So those are herbivores in an ecosystem under different sets of environmental conditions. So we're going to watch a video that shows us how to use the simulation, and then we'll do the simulation ourselves. So I just have to find the video. I think this is the video. It is. So I'm going to try to skip ahead about 30 seconds because he gives some instructions that we don't need. And then we'll jump into, this is what the simulation looks like. A little bit. I'm just going to hit play and see if it goes.
And when you do that, you will see this interface appear in your browser window. Your model is now ready to run a series of experiments. You may do that by first initializing the model using the Setup Reset button. Every time you press this button, you'll see the world shown here change based on the settings assigned to it in the sliders around the interface. To run the model, press the Go Pause button. Notice that when you do this, the agents in the model start to change. We see the buffalo moving around. We can see patches of green growing larger. These are patches of grass that grow based on the amount of rainfall that they receive. The grass patches will grow until the entire patch is filled. That patch will remain filled with grass until a buffalo moves over it. When that happens, the grass will be consumed by the buffalo, and the buffalo will gain the energy from that food and store it in its body. Grass will grow back in time, given enough rain. As buffalo move around, they burn food for energy through cellular respiration. This causes the amount of stored food as fat in their body to decrease. When they run out of stored food, they'll die. In the current setup of the model, the rains are falling on the right side of the model, which according to this compass shown here is to the north. We can see where the rains are falling based on the blue tint to the patches. And so a little bit of these rains are falling on the right side of the middle region of the model. If buffalo store up enough food, they can reproduce, passing on some of that stored food to their offspring. Reproduction in this model is simplified so that a female will give birth to an offspring without a male if they have enough stored up food. As you run the model, you'll see the monitors and graphs for the size of the populations changing. If you want to speed up the simulation run, you can do that by sliding the speed slider to the right.
We'll definitely want to do that because this
when you
is
do
a
that,
slow
the simulation runs in fast forward mode, skipping many of the updates to the view of the world. By changing the speed back to normal speed, you can see the state of the model back running in real time. And it may be useful at times to pause the simulation to see what the state of the model is at exactly that single point in time. To do that, press the Go Pause button again. Let's take a look at the state of the model at this point in time. Notice that here I can tell how long the model has run for, and here I can tell how many buffalo there are in the world, 39. I can also tell how many buffalo there were in the past by hovering over the graph and seeing what the value for the size of the buffalo population was. Notice that its high point was about 55 buffalo. Its low point was around 10, what I started with, but the model has leveled off between about 35 and 45 buffalo. I can resume the model run again by pressing Go Pause, or I can reset the model run from the start by pressing Setup/Reset. Various investigations can be done with this model, but they'll require you to adjust these sliders, these drop-down menus, and switches to change the state of the model. And many of those changes will only take effect when you press Setup/Reset. Good luck.
All right, so that gives us sort of an introduction, and I want to back up for just a second.
Pressing Go Pause.
I'm going to pause because we're going to want to come back and look at his graph in just a moment. But we'll pause right there. Let's go to what we're looking at here. So now we've watched it, and it says you saw the initial population of 10 buffalo grow and then level off around a stable population between 35 and 45 buffaloes. I'm sorry, you guys, that Cami always, when it's two Fs, it has trouble reading two Fs, so it looks so weird, but about 40 on average. Once enough time passed. So let's go back and look at his diagram for a moment, this one. Notice that, can I make it bigger? Oh, I can. All right, so it went up to above 50 and then it drops back down, but then it starts leveling off sort of. It's still always fluctuating a little bit, but we said that it's fluctuating right around 40, between 35 and 40, mid 40s is what it's usually fluctuating at. Okay, so let's go back to see what they need us to do. So number 9 says, what causes the population size to grow? Well, there's two things really that are causing the population size to grow. So as animals eat, they have more babies. So the more food they have, the more babies they're able to have, and that causes the population size to grow. Number 10 says, why doesn't the population size level off completely? Why isn't it a flat line? Why do the numbers continue to fluctuate up and down? And I'll give you a second to think about that. What would make a population go back down again? Hopefully you figured out that there's still going to be, even if there's plenty of food, there's still going to be some animals that are dying in addition to animals being born. So the numbers fluctuate, change, we'll say change, that's easier to spell. The numbers change as animals die and are born. That causes the population to be going constantly up and down as animals are dying and as they're born. All right, so it says predict. Now I want to remind you here really quickly. This is his simulation. He started with 10 buffalo, and this is what that graph looked like. It went up to just about a little over 50 and then came back down to probably in the 30s and then ended up in the 40s. So you're going to make a little prediction. What if we do the scenario, which we're going to, we do the simulation, but we start with 50 buffalo. So we're going to begin right here. What if we start with 50 buffalo? So what do you predict the shape of the population graph would look like over time? So by the time we get to, now just be aware with time in this model, it's not minutes, hours, days, months, years. It's none of that. They call it clicks. So it's no set amount of time. It's just time passing in the computer model. So we're going to follow it to 2,000 clicks. Who cares what that represents? So you're going to start with 50, and I want you to see his model again. So they got to 2,000 right here. This is 2,000 clicks. So what do you think your graph is going to look like if you start right there? How is that going to impact what happens to your population? So go ahead and draw it. I'm not going to draw it for you. So everybody's is going to be different. And please don't be worried about being wrong. Just what's your guess? Make a sensible guess. Use your brain, but if it's wrong, that's always more fun. We like it when it's wrong because then you're learning something interesting. You thought it was going to be this way and it turned out to be that way. So draw a graph right here, grab the drawing tool and draw what you think is going to happen. Are they going to go down first? Are they going to go up first? Are they going to be straight across? What do you think is going to happen in that graph? So take a moment to do that. Okay, and then number 12 is a fun thing to guess. It's cool. How do you think the size of the population that we're doing will compare to what we saw at the end of the video? So let's see what we saw at the end of the video. At the end of the video, it ended up, what is that? About around 40. I'm just going to say around 40. It's been fluctuating between 35 and 45. I can't tell what that is exactly. So somewhere around 40. That's where his ended. So we started at 50. What are you predicting you'll end at click 2000? So all you need to do right here is to put a number. Do you think you're going to end up with 0 animals? Do you think you're going to end up with 100 animals? Do you think you're going to end up with 60? Put a number there. And so it'll be interesting to see how that compares with his scenario. Okay, so hopefully you've guessed. I don't think that takes very much time. So let's go ahead. We're going to go ahead and open the browser. Now, you can't do that from the video. So if you want to do this yourselves, you absolutely can. I'm going to do it for you today, just so that you can see it in the video and be done with it. But if you want to try doing the simulation and messing around with some of the sliders, it's right here where it says investigation number 1. That's the link to the simulation so that you can do it yourself. Okay, so I'm going to go ahead and open it right now. I know what all these things say, so you need to read it in order to be able to do it. But I'm going to go ahead and click it. And I will tell you that this unfortunately takes a long time. So I've already got it. It's set at 10. What am I screwing up? I need 50. Where's my 50? Buffalo to add. Why is it a 10? I don't know why it was at 10 there. It should have been right in the middle, should be 50. That was confusing to me. Okay, so we're going to start with 50 animals. And so I'm going to go ahead and hit setup reset. So there are my 50 animals, and we're just using this one plot of land. We will get lots more complicated once we start getting the hang of using this simulation, but we're just starting in this one plot of land for right now. And I'm going to go ahead and hit go, and they're going to start eating. And so I've got this, this model speed, this blue line here, I've got it as fast as it will go, because this model takes a lot more time than the bacteria model did. So I'll talk you through it for a few minutes, but we might just have to sit and watch it. And feel free to speed up the video, my video, if you want. Over here, what we're doing is we're looking at how many buffalo there are. So we're watching what happens. We started with 50. We're going to take it all the way. It's going to go actually past 1,000 to 2,000. I cannot go away from this particular view. Let me pause for just a second, actually, because I can. It just stops the simulation. Okay, so you are going to show exactly how it turned out when we're all done. Okay, I know what we're doing. Okay, so we'll keep watching it here, and we'll let it get to 2,000 or maybe 1,500 animals. What I see interesting was this part of your hypothesis of how this graph was going to turn out. They're going down really fast. There were a lot of animals. That kind of makes sense, right? If we start with a lot of animals, there's going to be a lot less food available for them. So can they survive it? Well, it looks like they're starting to level off. So maybe their population went way down. And so once their population goes down, then the grass has time to start growing again, right? So now maybe their population will level off. Maybe it'll start increasing if there's enough grass. If the females are getting enough food, then they get to have some babies. So we'll watch it for a little bit. Feel free to speed this video up right now. There's nothing I can do about it. I have to sit here and watch it, but you could fast forward until we get near the end here. I see the numbers are increasing They're going up again. So there's been enough food for the animals to start reproducing again. I wonder how high they're going to go. Already it looks like it's leveling off. We're getting to about 40. It's certainly slowing down. It's not the population's not increasing as much as it was before. Oh, look at it, went just over, just to 50 for a second and then back down again. There, it's at 50 again. So we're about halfway through, roughly halfway through our simulation. So it'll be another 2 minutes and we'll be done with the simulation. I'm going to get a drink of water while I'm waiting for the simulation. Unfortunately, I wish that I could switch tabs, but if I switch tabs so that we could work on something else or whatever, then the simulation stops while I'm not on the tab. And that's really too bad because it's a slow simulation. It'd be nice if it would work in the background while we were doing other things. I see that it went up to 50, but then it started coming back down again. So we're not going over 50 much. That's interesting. What did you think would happen? What was your prediction for this graph? How did you think it was going to turn out? How did you think it was going to turn out if we started with 50? Did you think we were going to end up with more animals than he did when he started with 10? Or did you think we were going to end up with the same number of animals or fewer animals? All right, well, we're almost there. It'll take maybe 30 more seconds. I'm watching the graph over here, and I'm also looking at the time. We want to get the time to at least 1,500. 2,000 is better than 1,500, but at least to 1,500. But this is taking a long time. I guess you can fast forward, so I may as well be patient because you can just zip through it. Very slow. All right, well, we're up to 1,500. Maybe slow the video back down again so that we can talk now and answer some questions. So we've gotten over 1,500 now, and it seems like we can pretty much guess what's going to happen. So we saw an initial decline. We saw them go all the way down to 22. It looks like that's the lowest number. And then they gradually increased, probably because the grass started growing again since there weren't very many buffalo eating it. They got up to, looks like 49, maybe 50 in that area. And then they're just kind of fluctuating in that same range. Remember in his scenario, I'm going to let it keep running it. Oh, I can't. It doesn't run in the background. Remember in his scenario, it kept staying between 40 and, between 45 and 35. So I was like right around 40. And sure enough, ours ended up exactly the same. Look at this. Ours ended up, right in that 45, 35 range. So here's 40. I like to think that it's right around 40 that it's averaging. So there you go. Very similar results. So let's go back to our sheet. And it says, record the shape of the graph and the size of the population at this point on the graph. So go ahead, I'm gonna show you the shape of the graph again, and I'll just make it really big. There we go. And then you can just draw that graph. I may as well pause it. Give me just a second to pause it. There we go. So this is what the graph looks like. So it never goes above 50. There's a big dip, so 500 clicks is where it's the lowest, and then before 1,000, it's back up to 50, and then it just wavers around 40 after that. For the rest of the time, it wavers. The last one we see here, the last one is 41. It looks like the last population was around 41. Okay, so hopefully you've had a chance to draw this and record the size of the population. So around 1,500, it was around 41, so just below 50. So you might draw something. I'm going to draw it sloppily. I want you to do a nicer job than I'm drawing, but you would have done something like this and then back up. Whoops, I didn't do a very good job at that. And somewhere, oh my gosh, well, whatever, somewhere around 41 in this area. That was really bad. I need to undo that. Shameful. Hopefully you can draw with your finger better than I can. I'm not using my stylus because I'm not on my Chromebook right now. All right, next it says, on your own, repeat steps D through G, changing the buffalo to add number. Record your graph below. Be ready to share your graph with the class. So what that means is you can do the simulation yourself. Remember that I have linked it right here and you could do your own investigation. But to save us time, and because you're not in class right now and we can't all share our graphs, I went ahead and did the simulation, and yes, I had to sit around a lot with all kinds of different populations. So I want you to look at what I'm seeing and look at what I'm showing you, and I want you to see if you notice any patterns. So this is starting with just 10 buffalo. This is starting with 10 buffalo. And here we have, this is what the man in his simulation did. He started with 10, it went a little bit above 50, and then fluctuated right around 40. Okay, that's starting with 10. Starting with 25 buffalo, it dipped a little at first, but then it went up to, right around 50, and then, fluctuated around 40 again. Here's 50. This is the one we just did. Very similar. It was a different simulation, but the results were almost identical. It dipped down the first 500, made it up to almost 1,000 at 1,000 clicks. It was around 50, and then it went up and down again, right around 40. The next one at 75, it dipped, enormous dip, way down, but they recovered. I wonder what's going to happen at 100, you guys. They recovered and came, interesting, back up to 50 and then fluctuating in that 40 area again. Okay, here's 100. Oh my goodness, it was down to, I think if I remember, this was 2 individuals, 2 females left to have babies. But they did it. They had their babies, and by a little bit past 1,000, they reached over 50. So that's an interesting pattern to look at also. How long did it take them to get over 50 when they come back? That one was at right about 1,000. This one was a little bit before 1,000, and the 100 was a little bit after 1,000 when it hit its next peak. But again, it goes back down and then fluctuates back up at, right around 40. So let's go ahead. You need to draw one of them. I don't care. Once you draw the 100, I'll just leave it here. So on your student activity sheet, you're supposed to draw another one. So I'm going to go back to it. I'll show you. So in this one right here, you can draw any of them. I don't care. But I'll show you the one that was at 100. Where'd I put it? The one that was at 100. So it starts at 100. And by 500, there were 2 animals left. By over 1,000, there's a little bit, by 1,000 clicks in time, there's a little bit over 50 animals. And then it dips down and comes back to around 40 animals. 40 animals seems like an important number here. All right, so going back, hopefully you've had a chance to draw that. So now it says record any patterns you notice in the stability of the ecosystem. So the first thing that I notice is that once the population stabilizes, which takes it a little bit of time. Once the population stabilizes, it tends to fluctuate fluctuate, there we go, around 40 animals. Sometimes it's a little lower, sometimes it's a little higher. The other pattern that maybe we just noticed, I hadn't noticed this before, is when there were lots of starting animals, it took the population longer to stabilize. So it took the population a longer amount of time to get to that 50 and then fluctuating around 40 again. So those are the observations I noticed. Put it in your own words, do whatever you want for that section. All right, now that is all you need to do if you want a C. So if you want a C, have your questions answered up to through the observations. If you would like to go for a B or an A, let me get that out of the way, then you need to answer these last 3 questions. I'm not going to answer these questions for you, so you can go ahead and try to answer them, but I will mention right here, let's see, do I have a highlighter somewhere? Is this a highlighter? Yeah, I will mention this phrase right here. It might be a new phrase for you, carrying capacity. So let's just look at question 15. I'm not going to say much more than that, but how is the idea of carrying capacity related to the outcomes you observed in this model? So carrying capacity is the maximum number of animals that the environment can support before they start running out of food and dying. So we know, for example, by looking at this graph, we know that the environment can't support 100. Look what happened. Death, 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 death. 98 animals died before they were able to start reproducing. And why were they able to start reproducing? Because the plants started coming back again. They were eating well and they could start having babies again. So carrying capacity is the maximum number that the environment can support and keep them alive. They won't die of starvation. So that gives you a sense of what that particular term means. So how is the idea of carrying capacity related to the outcomes we observed in this model? Was there a carrying capacity in this environment? Around what number is the carrying capacity? What's the number of animals that can survive without everybody dying off? What's a good number in this environment? What's their maximum number without dying? I mean, a few always die, but without a mass die-off, what's the maximum number? So if you're going for the A or a B, then answer 13, 14, and 15 independently, and then go ahead and get it submitted. Let me know if you have any questions, you guys. See ya. Oops, I can stop it here, can't I?